Welcome to the first ever CoVidLog or coding video blog. And initially I wasn't sure what I was going to do, but since it's about coding, why not just talk about a coding topic? Today I'll be talking about binary jumping. And although that's probably not the formal name for it, I think it's pretty cool because you can do a lot of stuff with it. So what is this? Oh yeah, I drew this before. Basically, you just go in descending powers of 2, starting from whatever number makes sense. And you go all the way down to 1. Because once you divide by 2 again, you end up with a fraction. And you can't do that. So what can you do with the fact that you can go down in powers of 2? Well, for starters, basically, since you're jumping by all powers of 2, you can reach any single position. Let's say if you're on an array. And why is that? Well, any number on the array is just an index value. And that index value can be written as binary. So let's say we want to get to index 7. So in binary that would be 4, 2, 1, which is not that, but I don't know how to erase this. So let me just write it here. So that's what 7 is in binary. So in order to get there, you just make a 4 jump, a 2 jump, and a 1 jump. And you can do that with basically any index. So that's cool. Now, how does that relate to binary search? Typically, when you do binary search here, let's say just for a really simplistic example, you want to find the first one in this array. And note that everything after the first one is also a 1, so that's just implied from the problem. And with binary search, you basically keep on splitting the array in half until you get to your answer. Now with binary jumping, you start at the first index and you take jumps to the right in decreasing powers of 2. Note that it doesn't work for increasing, and I might get to that later, or I might not, who knows. So if you want to jump to the right, you can't go out of the array, right? So that's your upper bound here. And since the array has length 9, our farthest jump that we can make is 8. So let's try jumping 8 to the right first. Keep in mind our current position is here. So we get here, and what does that tell us? It tells us that we jumped to a 1, which means we either reached our target or we overshot it. The problem is that we don't know if this is actually the answer or if it's somewhere to the right of it. So because of that, we can't exactly do anything here. So we're just going to assume that we overshot it. That means that we don't make the jump to 8. Instead, we go down to 4. Also, this might seem weird. Why aren't you jumping to the thing after that? But if you do, you don't really have any idea where you want to go. And instead, if you just make it so that your position is always on a 0, after you finish your binary jumping, you're going to end up at the last 0. So then if you add 1, you're on the first one. Oh, I didn't close this. Oops. Alright, so we make a jump of 4. 1, 2, 3, 4. Now we're here. And since that's a 0, we can just move our pointer over here and take our next jump. That's a 2. And if you jump to 2, well, you end up with a 1. And since the computer doesn't know whether that's overshooting it or not, it's just not going to go there. And finally, you end up with a jump of 1. And since that's a 0, you jump there, and boom, that's your answer. Well, that's not exactly the answer, because you still have to add 1. But since you know that's the last 0, the next position is going to be the first one. And that's binary jumping in a nutshell. There is one special case where if you have all 1s and you want to find the first one. Well, the problem is This algorithm, if you can call it that, assumes that the position that you're starting on is a 0. In this case, it's not a 0, it's a 1. So you're just gonna need to put a check in the beginning that checks whether or not the first thing is a 1 or not. And if it is, you can just return 0 as your answer, because there's nothing to the left of the 0th index. Alright, if you want to see an actual implementation of this, here it is. This one is slightly different in the fact that you want to find the actual target number instead of just finding like the first one in a sequence of ones. And it's basically like the same thing, because if you want to target, you split this thing into like 2 zones. Everything that's less than the target and everything that's greater than or equal to it. That way, this binary jumping thing gives you the index right before where the target is supposed to be, since it's part of the second zone. And then once you do that, you just add 1, and that should be your target value. And it says you must write an algorithm with log-in time complexity. And binary jumping does that because it goes in descending powers of 2. So as you can see here, this log thing just finds the highest power of 2 that's less than the length, and then it just goes down all of the powers of 2, checking if you can jump that distance, assuming it's still, that distance is still in the length of the array. If that point is part of the first zone, then you can jump there. And at the end, I here just represents the last value in the first zone, meaning the last value in the group of numbers that's less than target. And then if I is actually at the end, or if I plus 1 doesn't equal target at all, which could happen, then target doesn't exist. Else you just return the element to the right of target. And of course, yeah, this works because I ran it before. But you know, it's pretty fast. And it also doesn't require that much memory, which is cool. Alright, I know in the beginning of the video I said that you could do a lot of other things with it, but I realized that just explaining binary search took like 5 minutes, so you know, I'm not gonna go that far. But I might cover this later. Binary jumping can also be used to find things like the nth parent. Alright, you know what, I'm just gonna write some text. You can get like the nth parent of a node on like a tree or something. And that, with some log-in pre-processing, or in-log-in pre-processing, you can basically jump up the tree in powers of 2. And with binary jumping, you can utilize that thing that you had from before. Lowest common ancestor, that's another thing that binary jumping is great at. Also, when you have suffix arrays and you want to find the longest common prefix of 2 substrings in your suffix array, binary jumping is good at that as well. You just need a bit of adaptation. And like, if you already know all of this, I don't know, you're just like better than me, I guess. So yeah, that's all I have for today. Let me just flip this. There you go.